Hello, and welcome to lesson 6.3, where we are going to be talking about intramolecular bonding versus intermolecular forces. And actually, the bonding we're going to sort of review a little bit, but that's what we have been talking about, right? The chemical bonding. But we want to discuss how it is different from these intermolecular forces. And then we'll define what those intermolecular forces are. Frequently, you will see this abbreviated as IMF, intermolecular forces. Anyway, so just some review from 6.1 and 6.2. Remember these intramolecular forces, intermoleculars, two different molecules, right? Um, they hold the atoms within a molecule together, or the ions in an ionic bond. Okay, so this is covalent. This is ionic bonding, right? We've talked about both those types. So when we say these ionic and covalent bonds are examples of these intramolecular bonds, okay? They are very strong. We will do a lab that will show this, a simulation. But these interactions are super strong. Okay? The energies needed to break those bonds are high. We talked about that in the last section, right? You looked at some of those numbers. It takes a lot of energy to break these bonds. Okay? And then when they do break, remember, different molecules are formed. Okay? So the whole chemical composition is changed. Like in that example of the hydrogen and the chlorine, both of those things are gases. But then when we combine the two to get hydrochloric acid, it is a liquid, right? So the whole chemical nature is changed of these things, becomes a completely different thing. The biggest example I have of this, and I know I've talked about this before, is salt, right? Salt is sodium chloride, right? Sodium chloride. Sodium by itself, very dangerous metal. It explodes. If it even touches the water in the air, it can explode. Very dangerous. Chlorine gas, also incredibly dangerous. Right? They used it as a chemical weapon in World War II, Vietnam, both of them. Whenever it will kill you if you breathe it. It is very dangerous. But if you put those two things together, sodium and chlorine, you get salt. Y'all eat it every day. Look, I have a shaker of it right here on my desk. Salt, right? Something that is in most of the food that you eat. Totally not harmless, right? So the chemical composition completely changed from something dangerous to dangerous things to something we all eat every day. All right? So these are intramolecular forces. Right? Remember, they're attractions between molecules or between atoms in different molecules. Okay? That's bonding. Okay? Now, when we talk about these intermolecular forces, these are forces inside the molecule, and they are responsible for controlling the properties of liquids and solids. So they control those properties, like when you're boiling water or freezing water. That is when these IMF, intermolecular forces, come into play. There are three basic ones that we're going to talk about. You see them over here. One is called a dipole-dipole interaction. Then there's a hydrogen bond. And then the other one is called London dispersion forces. So we're going to write all those in. So dipole, we will define all these, so don't worry. Dipole interactions, hydrogen bonds, and London dispersion forces. These are the three examples of intermolecular forces that we're going to be talking about here in this lesson. So, intermolecular forces are a lot weaker than the intramolecular bonding. Remember, we talked about the force there was very high. So they require less energy to break. It requires a whole lot less energy to boil water than it does to make water, right? So when these intermolecular forces are broken, basically what's going to happen is they'll change state. Liquid becomes steam. So those bonds get disrupted. Things get moving around a lot faster, and you get a change of state. So when these intermolecular forces are broken, right, the chemical composition of something is not changed. When you melt ice, it's still water. It's not two completely different chemicals composition. Right? It's still water, whether it's ice, liquid, steam, still water. So the chemical composition doesn't change at all when you break these intermolecular forces apart. All right. So let's talk about some of them in more detail, starting with these dipole-dipole interactions. Okay, is first of all not a hydrogen bond; those are something completely different. But basically, molecules that are asymmetrical, they are called polar molecules. We will talk about this in a little more detail in the next lesson. But they are not symmetrical. Like this is not symmetrical. If there were two more hydrogens, then it would be, right? Hydrogen chloride, not symmetrical. So they're called polar. They're also, basically what happens is the oppositely charged ends of the molecules attract each other. Okay, and those are called dipole-dipole interactions. Because they're polar molecules, let's define that really quick. Polar means they have a positive end and a negative end. So you can see here, that's what these little things stand for. See that this is a positive end. Here with the sulfur is the negative end. And what happens is the negative end of one molecule is attracted to the positive end of another. And that is what holds them together. So if you look at a cup of water, what is holding all those water molecules together is the fact that the oxygen end of the water So I'm going to totally rewind what I said, and I don't know how to cut it out, but I want to talk about this sulfur dihydrogen, not water. I got confused because it's two hydrogens. But the positive end and the negative end is what holds these two things together. Same with the hydrochloric acid here. The hydrogen is a positive end, the chlorine is a negative end, and that is what holds them together. The positive charge and the negative charge keeps them together. So polar molecules that have these dipole-dipole interactions have higher boiling points. So it takes a lot more energy to boil them and to break these bonds than it does with other molecules. So dipole-dipole, what you need to know is that it is polar molecules with a positive end and a negative end being attracted to each other, and they have relatively high boiling points. Hydrogen bonds are the other type of bonds. Hydrogen bonds usually occur when there is, a hydrogen, obviously, but the oxygen, nitrogen, or fluorine. those are hydrogen bonds. Okay, so they're a special type of dipole-dipole interaction. That have just a super strong bond. So those are called hydrogen bonds. It is oxygen, nitrogen, fluorine bonded with a hydrogen. So see here, fluorine, oxygen, nitrogen, all bonded to hydrogen. Those are the hydrogen bonds. Okay. The reason that these bonds are stronger is because the hydrogen's electrons are pulled very strongly towards the oxygen, nitrogen, or fluorine. Okay, so oxygen, nitrogen, and fluorine are the most electronegative atoms that there are. Electronegative. Remember we talked about electronegativity in Unit 4. But that is an atom's ability to pull in electrons, right? So oxygen, nitrogen, fluorine in that upper right-hand corner of the periodic table are the most electronegative. So they form these stronger bonds called hydrogen bonds. So they will have high boiling points than the dipole bond. So we can just, this is a special dipole-dipole bonds involving fluorine, oxygen, or nitrogen. Right? So those are the hydrogen bonds because those more electronegative things. Now, how do these bonds affect boiling points? Boiling point is the point at which a liquid becomes a gas. You've all boiled water, you've seen that, right? So the boiling point is determined by how much energy is needed to break these intermolecular forces between those molecules that are being held together. The mass, size, and shape of the molecules also affects it, the boiling point. But the biggest factor is those intermolecular forces. Okay? If they're strong, the boiling point will be high. If they're weak, the boiling point will be low. It takes less energy. Remember, heat is just energy. So it takes more energy to break the strong bonds than it does the weak bonds. Well, that just makes sense, right? It takes more energy to break something stronger. That seems to make a whole lot of sense to me. Water, hydrogen bonds are stronger than hydrogen sulfide. So even though they look the same, right? Like look here, water, hydrogen sulfide. Two hydrogens, this one's a sulfur, this one's an oxygen, but they basically have the same shape. But this bond here, because of oxygen's electronegativity, means that water has a higher boiling point. Okay, so we can look here in our pictures. Here's liquid water. You see all these molecules held together with these hydrogen bonds. 100 degrees Celsius is the energy we need to add to get steam, where those hydrogen bonds are broken and you have individual molecules. Hydrogen sulfide, these dipole-dipole interactions holding them all together, when it's liquid, its boiling point is negative 60 degrees Celsius. So not very much, versus 100. That's a whole 160 degrees away. So that's a huge energy difference. But that is the temperature that this hydrogen sulfide boils at Obviously, it's a gas at room temperature, right? But those hydrogen bonds get broken, and you have the gas. Hydrogen selenide, same type of thing. It's got these dipole-dipole interactions holding it together. Negative 42 degrees Celsius will break those bonds. So again, it is a gas at room temperature, right? Liquid at room temperature, gas, gas. Because it doesn't take a whole lot of energy to break a hydrogen or to break a dipole-dipole moment, but it takes more energy to break that hydrogen bond. Let's see how the mass factors into that. Remember I said up here the mass can affect it. But as mass increases, boiling point normally increases. So you can see that oxygen mass increases, boiling point normally increases, right? Hydrogen sulfide has a lower mass than hydrogen selenide. If you pull out a periodic table, how many times do I record these videos and say, oh, if only I had a periodic table? And then, but still, oh, here it is. But sulfur has a mass 32.07. Selenium 78.96. So it is heavier, right? Sulfide has a lower mass than selenide. It also has a lower boiling point, negative 60 versus negative 42. Less energy is needed to boil the hydrogen sulfide than the hydrogen selenide because it has less mass. The water, which has actually the least mass, takes the most energy because it's a different type of bond. Right? This is the hydrogen bond versus these two are that dipole-dipole. I'm just abbreviating it. Mass does affect them, but the hydrogen bond is still always stronger. All right, let's very quickly. I know this is a longer lesson than usual, but it's got a lot of stuff in it. The last type of intermolecular force is called a London dispersion force. Okay, electrons not drawn to scale, just FYI, so you can see them better. So, as we just talked about, dispersion forces are the weakest intermolecular force. So, these are the weakest, these London dispersion forces. They can happen between all types of molecules, polar, nonpolar, doesn't matter, right? What happens is we all know that electrons around the atoms are constant motion. They're always moving around. They don't stay in the same place. They're not always symmetrically distributed. They could all be on one side, all be on the other. It is very random, this motion, right? And it is constant motion. We call that them moving in the electron cloud. We've all heard of that before, right? So, at any instant in time, there's the possibility that there can be a temporary dipole. A temporary dipole. So this temporarily all the electrons are on one side, making a positive end versus a negative end. Right? So that would be more electrons concentrated on one side and less electrons on the other side, making a more negative side and a more positive side. Right? So let's look at this picture. Here we have oxygen and carbon. Here's all the electrons that they share in this cloud, moving, 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 moving. You can see how they're evenly distributed throughout the molecule. No dipole, even distribution. But what can happen is if all of them sort of transfer to one side as they're moving, you just get a brief, temporary, uneven distribution. So you have all your electrons over here, which gives this a positive positive end and a negative end, because those electrons have kind of all congregated on one side. Because they're constantly moving, they will move away from that. But temporarily, there's a negative end and a positive end of this molecule. So with these London dispersion forces, what happens is when atoms are very close to each other, the electrons in one molecule that has a temporary positive and negative, electrons with a temporary dipole, can distort another molecule's electron cloud. So this is called, another term to learn, induced dipole. Because it was brought about by the one atom being off kilter, induces the other to be off kilter, right? So these temporary dipoles only there for an instant, but that instant can affect the chemical properties of these nonpolar molecules. So it can just kind of throw everything out of whack for a little bit. And that's these London dispersion forces. Sometimes they're called instantaneous. This will be hard to spell. Instantaneous dipole. Erasing. Dipole induced forces. Instantaneous dipole induced forces. So here's a picture of how that happens. We have this electron cloud around this molecule here. Temporarily, all the electrons are gathered over here because they're just moving around. You know, you've seen that happen in a room before when people are kind of moving around. Sometimes they congregate on one side, move to the other, spread out evenly. Right. So the electrons are temporarily kind of congregated over here, which makes this have a positive end. So what that does is it draws the electrons in this other molecule towards the positive. Remember, they're negative. So they get drawn towards the positive here. And what we have is then two molecules temporarily bonded together because of this electron distribution factor. All right, so to kind of offset that poorly distributed electrons, temporarily they get bonded together. So that's basically what happens in a London dispersion force. Larger molecules have stronger dispersion forces. Right? The shape also affects it. If two molecules have the same mass, but one of them is longer, the longer molecule will have stronger forces, which makes sense because those electrons get further away. There's a more positive end, so it's more attractive. Right? So the longer it is, the further away the negative is, which causes a stronger force. So chlorine has a weaker length, negative 34 degrees Celsius, at its boiling point, when that dispersion force, when they start to break apart. Bromine, its boiling point is at 59 degrees Celsius. So it takes more energy than to break these very temporary bonds than it does with chlorine.